So we'll begin in about 4 minutes. Right on time. We'll start in about a minute. Hey, it's 9 o'clock. Today we'll be in section 8.3, part 1 on hydrostatic pressure and force. We'll look at some of the terms involved. So suppose a flat horizontal plate with area A is under a liquid at depth D. So a liquid like water or something, submerged under the surface and it's horizontal to the surface. Then the volume of liquid above the plate is V equals A times D. The area of the horizontal plate multiplied by the depth of the liquid. If we let rho be the density of the liquid and let g be gravitational acceleration, then the force of the liquid on the plate is capital F equals rho times G times A times D. So A times D is just the volume, rho is the density, and G is the acceleration due to gravity. And then the pressure on the plate is the force divided by the area, which is just rho times G times D. So this is force per unit area is how pressure is defined. In the international system, the mass density of water, which is rho equals 1,000 kilograms per cubic meter. That's the mass density of water. And acceleration due to gravity is 9.8 meters per second per second. The volume of a column of water, that's what I'm referring to. If we have a horizontal plate with area A at depth D, then the volume of water above the plate is A times D. So that's the volume is the area of the base times the depth. And it's measured in cubic meters in this setting. Okay, in the international system, unit of force is 1 Newton. So I have a typographical error. That isn't supposed to be a subtraction. It's a product, the result of multiplying. So it's 1 kilogram meter divided by second squared. So 1 Newton is 1 kilogram meter per second per second. And then a unit of pressure is 1 Pascal, which is 1 Newton per square meter. So a kilopascal is just 1,000 pascals. So kilopascal, unit of pressure. Okay, in the US customary system, the weight density of water is rho times G, and it's measured as 62.5 pounds per cubic foot. Okay, so the density of water times gravitational acceleration is 62.5 pounds per cubic foot. And the force is rho times G times the volume, or the area times the depth. And force is measured in pounds. And pressure is still force divided by the area. The pressure is measured in pounds per square foot. Okay, so that's the setting. We're going to consider vertical plates or vertically oriented plates submerged in some way in water. And we're going to discuss how to find the hydrostatic pressure on one side of the plate. Okay, a principle of fluid pressure that will come in handy for us is that at any point in a liquid, the pressure is the same in all directions. So we might need to refer back to that. So we're going to suppose that a vertically oriented flat plate is submerged in a liquid. And knowing the area of the plate isn't enough to determine the hydrostatic force on one side of the plate, because the hydrostatic force increases as the depth increases. It's pretty easy if the plate is horizontal to the surface, because the hydrostatic force is just the volume times the density above the plate. Okay, but this principle is going to help us at any point in the liquid. The pressure is the same in all directions. So I will attempt to describe how to find the hydrostatic force exerted on one side of a vertically oriented plate submerged in water. Okay, there's more than one way to go about it, but I'm going to use the XY plane rotated 90 degrees clockwise. So if I rotate the XY plane 90 degrees clockwise, then the positive y-axis is horizontal. So this is the y-axis for y values greater than 0. And the positive x-axis is pointing downward. So this is x greater than 0. So suppose we have some plate vertically oriented that's submerged in water. So the surface of the water is the y-axis, surface of the water. And we want to find an expression that represents the hydrostatic force on one side of that plate. Okay, well, what we'll do is we'll find the x interval so the plate corresponds to two x values. I'll call those values A and B. And we're going to subdivide the interval from A to B into n subintervals. And then we'll construct a rectangle for each of the subintervals. And we'll approximate the hydrostatic force on each of those rectangles for each of the subintervals. And then we'll add up those hydrostatic forces, and that will be an approximation of the total hydrostatic force exerted on one side of the plate. So let's just remind ourselves that force in this setting is the density times the gravitational acceleration times the area times the depth. So subdivide the x interval from A to B into n subintervals. Each of length delta x equals b minus a divided by n. So I'll pick out one of those subintervals here just so that we have something to look at. This will be from x sub I minus 1 to x sub I. And on that interval, we're going to approximate the area of the plate on that interval with the area of a rectangle. And the vertical side of this is delta x. And so to find the volume of water that is exerted on this horizontal plate, we need to know the area. So we need to have an expression for the horizontal side of that rectangle. Okay, so the idea,
yeah. How did you draw your rectangle? Did you
what's that?
How did you draw your rectangle? Did you use the midpoint of it, or just
Yeah, I'm gonna use the midpoint or a representative point to this interval.
Okay.
Eventually. But I'm drawing the rectangle big so that we can see it. But you know that we're going to let n go to infinity, so the rectangles get thinner and thinner and thinner. Yeah, so we'll get to that. But the idea is if you have a thin rectangle, even though it's vertically oriented, the hydrostatic force on that vertically oriented rectangle will be approximately the same as if the rectangle were horizontally oriented. You know, and especially so if the rectangle is really thin. Okay, so yes, we do want to know the depth that we're going to use, and I'll put that there in a second. But for now, suppose there is a function, suppose a function y equals, I'll call it w of x, measures the horizontal length of the plate from side to side. Okay, so if I pick an x value between x sub I minus 1 and x sub I, and I'll call it x sub I star, then the length of this rectangle is w evaluated at x sub I star. So I'll label that here. This is w of x sub I star. Okay, and the depth at this point is x sub I star. So let's just summarize what we have. I'll refer to a sub I as the area of that rectangle on the interval from x sub I minus 1 to x sub I. So the area of that is w of x sub I star times delta x. And the depth on that interval, I'll refer to that as d sub I, but the depth is x sub I star. And then we're treating rho times g as a constant. And so the hydrostatic force exerted on one side of the plate, which is just that rectangle, I'll refer to that as F sub I, and that's equal to rho times G times A sub I times D sub I. So I'm going to multiply W of X sub I star times delta X times X sub I star. And I'll rearrange it a little bit and write it as X sub I star times W of X sub I star times delta X. Okay, so we're going to get one of those approximations for each of the n subintervals. And so the total hydrostatic force exerted on one side of that, that's going to be equal to the limit as n approaches infinity of the sum of those n terms, I equals 1 to n of rho times G times X sub I star times W times W of X sub I star times delta X. And then the limit is going to be the definite integral from x equals a to b of rho times G times X times W of X dx. So that's all there is to it. The tricky part is in the individual problems, finding those components, as we'll see. Some of them are easier than others, but let's put this idea to practice in a few examples. Okay, so for this one, suppose a vertically oriented rectangular plate with dimensions 4 meters by 5 meters is submerged in water, where the short sides are horizontal and the top side is 2 feet below the surface. So find the hydrostatic force against one side of the plate. Okay, so suppose this is the surface of the water. And then we're orienting positive numbers downward for depth. So we have a vertically oriented rectangular plate. The short side is 4 meters and it's horizontal, so the long side is vertical. So 4 meters and 5 meters. So the top part is 2 meters below the surface. Oops, I switched units. I really want 2 meters. I don't want to have to convert 2 feet to meters. So 2 meters below the surface. So this point right here is a depth of 2. This is a depth of 7. Are we?
I did the same thing.
Okay, so we're all in agreement so far? All right. Okay, so again, we construct a rectangle. This is our, maybe I should have drawn it bigger, but anyway, our interval from x sub I minus 1 to x sub I. And we'll pick our representative depth as x sub I star. Well, this one's nice because the length is 4 meters. So our hydrostatic force, rho times g times the area times d, so A sub I is, this is F sub I for the hydrostatic force on this rectangle on that interval. So A sub I is just 4 times delta x, and the depth is x sub I star. So if we rearrange the terms a little bit, rho times g times 4 times x sub I star times delta x. Okay, so the total hydrostatic force is equal to the limit as n approaches infinity of the Riemann sum from I equals 1 to n of rho times g times 4 times x sub I star times delta x. And then the limit is the definite integral from where to where from x equals 2 to x equals 7. And then rho times g times 4x dx. So this one's pretty simple to compute. So rho times g, an antiderivative of 4x is 2x to the second, and then evaluated from 2 to 7. So we get 2 times 49, which is 98, and then minus 2 times 2 to the second is minus 8. And then we'll use the international system for rho and g. So 1,000. I'll leave the units out, and then the gravitational acceleration 9.8 multiplied by 90, and the units, you can write that as in newtons. Hey, did you follow that example? So this is about as easy as they're going to get. We'll look at some more challenging ones. Hey, this one, a vertical isosceles triangular plate with a base of 4 feet and a height of 6 feet is submerged in water, and the vertex opposite to the base is at the surface. and the base is horizontal. So the base is parallel with the surface. Find the hydrostatic force against one side of the plate. Okay, so we have our water surface. I'll just say surface. And a vertically oriented isosceles triangle. Something like this. The base is 4 feet. The height of the triangle is 6 feet. So the vertical distance, 6 feet. Okay, so from x equals 0 to x equals 6, so we're trying to find for a, a subinterval the hydrostatic force on a rectangle. So force is rho times g times the area of the rectangle times the depth. So for our subinterval, x of I minus 1 to x of I, we're just going to find a rectangle that approximates the area of that subinterval on the rectangle, on the triangle. Okay, so the depth will be at x sub I star. The width of that rectangle is delta x. And now, how are we going to find the length of that rectangle? Well, for this isosceles triangle, the perpendicular bisector of that isosceles triangle divides the sides into equal parts, and the height of this is 6. Okay, so at a depth of x sub I star, so this is a depth of x sub I star, we want to know what the length of this side is of that small triangle. So if I just give that a value a, and then we'll use 2 times a to be the length of that rectangle. Okay, so we'll use similar triangles. This triangle where the base is A and the height is x sub I star, it's similar to this triangle where the base is 2 and the height is 6. So I'll write this as A over x sub I star equals 2 over 6, which is 1/3. And then when we solve for A, we get A is equal to x sub I star over 3. And then 2 times that amount is just 2 times x sub I star over 3, which is what the length of that rectangle is. Okay, so our area for that particular rectangle is 2 times x sub I star over 3 times delta x. And we know that d sub I is x sub I star. And in this case, rho times g, the constant there is 62.5. Okay, so I think we can write down the force as the hydrostatic force is the limit as n approaches infinity of a Riemann sum from I equals 1 to n. I'll replace rho times g in this case with 62.5. And the area times depth, or the volume, is going to be 2 times x sub I star squared, because I'm just going to multiply x sub I star times that x sub I star, over 3 times delta x. And then when we compute the limit, we get f equals the definite integral. What are the limits of integration? 0 to 6. And I'm going to go ahead and multiply 62.5 times 2 and divide by 3. So I'll have 125 over 3 times x to the second dx. And this is a reasonably simple integral to evaluate. We'll take it a couple of steps further. 125 over 3 times x to the third over 3, evaluated from 0 to 6. So this is what? 6 to the third is 216. But I'm going to think of Is that what you need? Okay. I'm going to think of 6 to the third as 36 times 6, because 9 goes into 36 4 times. And so we get 125 times 4 is 500, and then 500 times 6 is 3,000. And then in the US customary system, force is measured in pounds, so 3,000 pounds. Okay, let's try the next example. And this one, the two ends of a water trough are semicircular plates, each with a radius of 2 feet. If the trough is filled with water, find the hydrostatic force exerted on each end of the trough. Okay, semicircular plates at the end. So radius 2. So I'm still going to orient the positive y-axis horizontally to the right and the positive x-axis downward. So I do it this way so I can measure depths as positive numbers. Okay, so our subrectangle, my drawing is off a little bit, but this part of the rectangle is supposed to be the same length as that part. So since this semicircle has a radius of 2 and the center of the circle is 0, 0, and this is the positive y-axis, then this part of this quarter circle is just y equals the square root of 4 minus x squared. And so for a value of x between 0 and 2, this function, y equals the square root of 4 minus x squared, gives us 1/2 the length of the rectangle. You see that? Okay, so if I'll just write down our force equation again, so I won't forget it. Rho times G times A times D. A is the area of the rectangle, D is the depth. Okay, so for x sub I star, if we're at that depth, then the area of that particular rectangle on that interval is 2 times the square root of 4 minus x sub I star squared times delta x. Delta x is the width of that rectangle. And d sub I is just x sub I star. And since we're measuring in feet, rho times g, I'll just replace that with 62.5. So F sub I, the hydrostatic force on that rectangle is 62.5 times 2 times x sub I star. This 2 goes from there, and then the square root of 4 minus x sub I star squared delta x. Okay, so the total force, if we add up all of those, that's equal to the limit as n approaches infinity of the Riemann sum from I equals 1 to n of all of those components. I'm going to leave it as 62.5 times 2 times x sub I star. We're going to need that factor 2 a little bit later. So square root of 4 minus x sub I star squared delta x. And then the limit is the definite integral. The limits are from 0 to 2. 62.5 times 2x times the square root of 4 minus x squared dx. Hey, I'm sort of running out of space, but if we think of u as, using the substitution rule, u is equal to 4 minus x squared, so du is negative 2x dx. We have a 2x, so we'll multiply by 1 in the form negative 1 times negative 1. So we'll get f equals negative, I'll bring the 62.5 out, negative 62.5 times the integral from 0 to 2. And then I'll rewrite 4 minus x squared. The square root of that is 4 minus x squared to the 1/2. And then negative 2x dx. So we get negative 62.5. And then we can compute the antiderivative. So we're going to get 2/3 times 4 minus x squared to the 3/2 evaluated from 0 to 2. Hey, if you're worried about this negative out front, well, it turns out that it's going to work out okay, because when we evaluate the antiderivative when x equals 2, we get 0 for that term, right? 4 minus 2 squared is 0. So negative 62.5, evaluated at the upper limit, we get 0, and then we're going to subtract the antiderivative evaluated at 0. So this is minus 2/3 times 4 to the 3/2, which is 8. So we get a negative times a negative. So negative 62.5 times negative 2 is positive 125. And 125 times 8 is 1,000, and 1,000 divided by 3. 1,000 divided by 3. Or 333.3 pounds for the hydrostatic force. Okay, let's at least start the next one, see how far we get. The length of each side of a vertical equilateral triangle is 2 meters. It is submerged in water with one side at the surface. Find the hydrostatic force against one side of the plate. Okay, an equilateral triangle at the surface, or one side is at the surface. So each side is 2 meters. Okay, so if we draw a perpendicular from this vertex to the base, it's going to divide that side into 2 equal parts, so 1 meter and 1 meter. So to find our rectangle, we're going to use similar triangles again. So when we're at a depth of x sub I star, we want to find the area of that rectangle. The width is delta x. Okay, so we know that this side is 1 of the big rectangle or big triangle. This side is 2. And what's the length of the vertical side? Square root of 3, right? Is that what you get? Square root of 3. Okay, so if we look at what happens when we're at a depth of x sub I star, so this is x sub I star, and we want to know what the value of A is. That will be 1/2 the length of that rectangle. And we have to use the small triangle here on the right. So what's the length of this part? So if the total length is the square root of 3, and if I take away x sub I star, then this is the square root of 3 minus x sub I star. And so to find the value of A, we'll divide A in this small triangle. A divided by the square root of 3 minus x sub I star is equal to 1 divided by the square root of 3. And so A is the square root of 3 minus x sub I star divided by the square root of 3. And 2 times that will be the length of that rectangle. So we're out of time, but hopefully you saw enough before this to know how to finish that part. But that's all for today.
Good.